Eames Shi and Delgado. Our project is exploring EEG-Image classification and EEG-based caption retrieval. The goal was to decode visual information from EEG and then test whether EEG embeddings could be aligned with clip text embeddings to retrieve captions. We used a low-speed subset of the MSS EEG dataset. It consists of 13 subjects, 5 sessions each, 26,000 total trials, and 20 balanced object categories. Each trial is a 122 channel by 500 time point EEG segment. We used a strict session-based split, sessions 1 through 3 for training, session 4 for validation, and session 5 for test. Task 1 is 20-way EEG classification. Task 2 is retrieval, giving EEG brand captions in clips text space. For task 1, we compared 3 architectures. First, a shared MOP baseline, then a CNN-only encoder with subject-specific heads, and then a CNN plus transformer encoder with subject-specific heads. The best task 1 encoder was reused for task 2B. For retrieval, we projected EEG embeddings into clips 512-dimensional text space and compared frozen clip, partial freezing of the last text block, and LORA. We also compared 3 loss settings, the full cosine plus info NCE plus cross entropy objective, cosine only, and no cross entropy. For classification, the MOP stayed at chance at 5% test accuracy, despite having 31.3 million parameters. The convolutional neural network only model involved improved to 6.19%. The CNN plus transformer reached 7.08%, and with light augmentation, it reached 7.38%. So the CNN plus transformer reaches about 1.4 times chance. So the main story is that inductive bias mattered much more than raw parameter count. The confusion matrix on the right side is noisy, but unlike MOP, it shows a real diagonal structure. Augmentation helped slightly, but did not change the overall conclusion. Before using EEG, we captured clip image to caption retrieval as an upper bound. On real image queries, clip achieved class-aware recall at 1 of about 0.97 and class-aware map of about 0.83. This shows the text space is well structured and is not the main bottleneck. EEG retrieval was much weaker but still above chance on class-aware metrics. In final comparison, the frozen model reached class map of 0.1190 and adaptive partial unfreezing improved that to 0.1274 and gave the best overall trade-off. LORA reached the second highest class-aware map of 0.1255 with fewer trainable clip parameters, so we treat it as our efficient PEFT alternative. For the ablation loss, we use class-aware map as the main retrieval metric. It shows that info NZ is essential. When we removed it, class-aware map dropped from 0.1274 to 0.0972. Removing cross entropy hurt much less, so it helps as a regularizer, but is not the main source of retrieval structure. The per class map plot shows that retrieval difficulty varies a lot across categories. Cat and person are easiest, while TV monitor and motorbike are clearly the hardest. The similarity distributions show that retrieved pairs shift right relative to random pairs. So the model is learning a meaningful alignment, but the overlap is still large. That explains why class-level retrieval works better than exact caption retrieval. Our main conclusion is that the bottleneck is not clip's text space. It is the EEG encoder's ability to preserve fine-grained semantic detail across subjects and sessions. For task 1, the CNN plus transformer clearly beat the MOP. For task 2B, adaptive partial unfreezing with cosine, info NCE, and cross entropy was the best balance setup, and LORA was a strong PEFT alternative. If we had more time, the next steps would be stronger subject-aware encoders, self-supervised EEG pre-training, and retrieval targets that are less brittle than exact captions. Thank you very much.